And we are going to move on to our next speaker, who is Rob Law. He is currently at the Brigham and Women's Hospital, Harvard Medical School in Boston. He's working with Sean Purcell. His title is Data-Driven Discovery of Dynamical Relationships within Electroencephalographic Spectra in Sleep. Welcome, Rob.
All right, thank you. And thank you to Gagna and John. Those talks were much more elegant than mine is going to be. The data that we're working with is kind of a mess. And this is the object of study here. It's a spectrogram from one channel of sleep EEG over an entire night. And our motivations here are epidemiology and population genetics to some extent. What we're really wondering is how we might collapse several hours of sleep EEG into an endophenotype. And to presumably get toward the question of, what aspects of longer time scale sleep dynamics are trait-like or disease biomarkers. This is very much work in progress. So typically sleep is staged where each 30-second epoch is assigned a category to non-REM, 1, 2, or 3, REM or wake. And often these spectra are averaged over, say, like all non-REM epochs to characterize sleep for an individual. But these spectra do vary slowly over time, even within a non-REM or REM episode or a sleep cycle. And we want to be able to quantify these things. And so in what we want to be able to do is kind of compactly describe how activities in different frequency bands interact or evolve over time. So this is a little bit of background here. So power in a given frequency band can usually be thought of kind of as a proxy for a density of events. So this is a sleep spindle here, and it turns out that on average, power in the sigma band corresponds with density of these spindles. And there are a number of these different kind of types of events: slow oscillations, delta rhythms, sleep spindles, beta events. And thalamic activity appears to be a common source for a lot of them. Which brings us to a model that kind of motivates us here. And this model poses that thalamic neurons can essentially be either in beta, sigma, or delta modes. And as sleep deepens, you go from beta to sigma to delta. As sleep lightens, you go from delta, sigma to beta. And they modeled this as a linear system of ODEs, or actually it was a Markov process, but which is kind of the same thing, but a little bit more restricted. What I think is a key insight here is that a dynamical systems model can describe how frequency bands interact. And so what we're going to do is try to fit ordinary differential equations to these data, the data that we have, and use these results as sort of a guide. But it's well known that individual spectral modes vary. So delta for you might not be the same as delta for me. And this is best studied in alpha, where you can see and this is a study from Kathy Kerr, that in individual spectral peaks can vary from 7 to 13 hertz. Possibly more. So the question is, can we characterize the evolution of band power in a population when bands are not even the same necessarily across individuals? And so what our approach is to characterize how these band limited activities evolve relative to each other. We're going to use non-negative matrix factorization to factor the spectrograms into frequency and time series factors, and that will give us a handful of time series that we can fit linear ODE systems to, okay? And so this slide I'm not going to be able to explain super well in the time that I have, but what we actually do here is 3 rounds of non-negative matrix factorization, first on the individual level, second on the group level, and then third again on the individual level to get frequency and temporal factors. But after this whole kind of reseeding process, these spectral factors are very consistent across individuals. I mean, almost like by design, but they also admit some variability. And without having kind of presupposed this, the 4-factor model yields delta, sigma, like a slow beta and a beta gamma component. And while 6-factors adds like a few more components as well. All right, so we've used NMF to reduce the frequency axis essentially, and now what about the time axis? So we're going to use these ODEs to reduce this dimensionality, or attempt to anyway. Just as an aside, the mean dynamics of sleep onset in the chat data set that we're using recapitulate some aspects of like the key aspects of the America Fortune data that use the classical delta, beta, and sigma frequency bands. Although ours is log transformed, theirs is not. All right, so what we're going to do first is we're going to smooth the data. We'll fit the dynamical system using the Cinder package in R. And essentially what we're doing is regressing X onto dx/dt. And the kinds of questions that we can get to are whether sigma power, for instance, correlates with a change in delta power, and rather than, just does it correlate with delta power itself. So this is what we wind up doing. This is what this kind of looks like. You have a smooth time series. The time series, the actual time series is below. It's all rescaled. And here, let's see, I don't really have a pointer, do I? Okay, but anyway, in the bottom left corner is the smooth time derivatives, whereas the modeled time derivative is in the bottom right corner. But what's kind of key to notice is that sigma and d delta dt are pretty well correlated in this case, and it turns out in many cases, like in this entire data set, the coefficient for d delta dt versus sigma is consistently positive across this population of about 400. So this data set yields a consistently positive correlation between delta slope and sigma power, and so this is consistent, I think, with the America Fortune work, and they also pointed to a negative correlation between beta slope and sigma power, which we also do observe. Okay, so, and this is maybe not that important, but like we can look at cases where the d delta d sigma is negative, and these seem to be like kind of aberrant cases that are where things just are kind of decoupled in a way that we wouldn't have expected, given like most of the population data, and there is still some overfitting here. So still trying to work out some of those bugs. But in summary, we combined non-negative matrix factorization and ODE fitting to investigate the spectral dynamics. And this is a flexible data-driven way to get some of these band-limited activities. And we found some consistent low-dimensional descriptors similar to those that were previously modeled. Although it's worth mentioning, we didn't find much evidence for any trait likeness in these coefficients. And so, yeah, the next steps for us, I think, are to regularize the coefficients, apply these to some other segments that haven't been studied before, the dynamics have not been studied before. And I think it's possible to apply this at some finer resolution, to maybe look at individual events, and to maybe segment out events that we didn't know existed before. Hopefully that would be really cool if that worked. And it's possible that this stuff can be applied to chronic recordings during wake. And the wishful thinking level is that for using this sort of thing for cross-species comparisons. And since you guys are the very first people to see this, thank you. That's about it. That's about all I have for that. So all right. That's all. Thanks.
Thank you. Those are beautiful graphs, I have to say. While we wait for questions, perhaps I could ask one. You were mentioning that there is individual variability across different people. I was curious about just the same person, but a different day, right? So when you are in looking at your sleep patterns.
Yeah, so some of this so far, we haven't really been able to find any consistency in the time factors. Presumably, in the spectral factors, those should be relatively consistent because they're known to be consistent for like using other sorts of other methods. So.
Mhm. Okay, all right, okay. You also mentioned the sleep component of the sleep in the kids component earlier. So I was wondering, do you have data in tracking babies or kids that go through sleep training? Like, do you see these kind of differences? Is this I would expect that those kind of data are probably pretty noisy. And so I was curious how your program would work for those things.
Oh, yeah. I mean, the noise is an issue. I mean, like a lot of these things are. I mean, all of these data have been run through by an expert. Like we just happen to have a large collection of that data, so it's like they have for instance, like basically like cut out segments of the EEG that just are super noisy. However, this does seem to work pretty well for pulling out wake periods. For whatever reason, the noise spectrum that is involved with all the EMG and everything is seems to be like taken care of reasonably well by this gamma component.
Mm-hmm. Okay, very cool. So we have questions coming in. So one question is, do you think the delta slope spindle power reflections, slow waves, and spindles coupling?
Yes, but what I think is may or may not be going on is that there's some feedback process between the cortex and the thalamus that's like that is using spindles to change delta power essentially. I mean, it's like it's possible there's something causal going on here. I don't know for sure.
Okay, right, okay. Another question is, can this method be applied to other EEG data, not sleep data? That is, what is the length of data required to do a similar analysis?
This I'm not exactly sure. It's we just happen to be able to. I mean, the segments that we're using are 30 seconds long. However, I'm hoping that this sort of stuff can be applied at like maybe the 1 second level or so. I mean, it depends on, I guess, the phenomena of interest, right, and your sampling rate and like that kind of thing.
Great. Looks like there aren't any other questions coming in at this point. I do have one more question since you were mentioning the cross-species comparison. There's a lot of EEG data in other rodent models, right? So have you tried to see if this would fit in? I mean, the sleep patterns are different, but do you think it works out this way?
Oh, I mean, I told you this is wishful thinking.
Yeah. Yeah.
But I mean, like what I do know is that at least from what I've read anyway, in rodents, the alpha frequency is different, right? So, I mean, like being able to kind of align these comparisons, like align the components would be, but then we'd have to kind of check to see whether the dynamics were similar in any way, and these kinds of things. It's like these homologies would not be easy to find regardless.
No, not at all. I don't envy the job, but I was just curious. So let me see. I think that's all the questions we have. Do the panelists have questions for each other? We have a few minutes. So if you guys want to talk about anything in particular about each other's work, you're welcome to do that. I find all of this absolutely fascinating. It's really cool that there are these models that exist for looking at data at this level. Talking about Gagana's question, and there was some aspect of this which is the higher, bigger question, right, in neuroscience in general, right? How does the brain contribute to the behavior? And you can think about vice versa. How does the behavior contribute to the brain? And you can think about consciousness and intelligence and sleep and all these meta-related subjects. So Jonathan, yeah, feel free to unmute and yes.
Yeah, Rob. So one question that was on my mind was, I mean, I know that a lot of these rhythms have been modeled at like neuron-specific levels of detail with different types of channels and all of those things. How do you see the relationship between your approach and those perspectives on those rhythms?
So right now, I think it's has to be vague right now. I mean, but what we do kind of know are that, things like spindles are not just assigned to, I mean, it's not just ion channels. It's really like kind of, there's a recurrent process essentially that's happening. And like my hope is that these processes are linked in this sort of, at the level of something that might be able to be described as a dynamical system. But yeah, but that said, I think part of dividing these things into different frequency bands is essentially like we're trying to, like, I feel like the frequency bands themselves are more indicative of often indicative anyway, of time scale than they are of necessarily like rhythmicity. Yeah.
Yeah, that makes sense to me. So you're sort of breaking it up and saying like, all right, this time scale is, it's got some set of ion channels that may be related to it, but we can lump that all together and just say, all right, let's model that with a higher level dynamical system, and then hope that, we can lump together the things associated with this time scale.
Mm-hmm. Yeah. And I would hope that these sort of these factors might be associated with, like multiple timescales on like a single process. But that would be, I mean, again, kind of wishful thinking. I do have a question for you too. So where is the circle, right? So like
I'm trying to write that right now into this paper. So I think that one strength of this framework is that it can talk about aperiodic temporal expectations too. It doesn't need a circle. It stays as on the real line. And you can just pose, to talk about periodic expectations, you can just make a periodic temporal expectation template. On the other hand, that leads to it's sort of blind to the ways in which periodic expectations can be different behaviorally and neurally. And it also leads to some weirdness, like if your confidence in your entrainment is low, then the system needs to know whether you're on beat 5 or beat 6 before it can resolve uncertainty. So yeah, I mean, ultimately the reason I didn't end up putting phase on a circle was because it did almost everything that I wanted it to without doing that, and because the math was harder. But that's a good question.
We have one more question. I believe this might be for Rob. So do you think we can compare non-human primates and humans with this approach? NHP might have more similarity to human data than the rodents, maybe.
I mean, hopefully.
Right.
I mean, this is really in its infancy. I mean, that said though, non-human primates might be difficult because we're actually maybe not. I mean, if we have many knights from a non-human primate, that would be one thing. But typically we need like a large population to kind of to condense some of these factors.